Very good morning, class. In the previous video, I have completed the Newton's second law and numericals related to the Newton's second law. Today we will discuss Newton's third law. Newton's third law of motion. Alright. Now what does it says? Newton's third law of motion says that if we apply some force on any body, then that body also apply the same amount of force to us. It means if I'm pushing this board with the force of 10 Newton on the back side, that means this board is also pushing me backward with a force of 10 Newton. Now you will say that how it is possible. Now for this, consider this example. You have an object placed on the table, right? Now you apply force on it. What will happen? This body will start moving in the direction of force, right? Because force creates the motion, right? Now if another force of same magnitude acts from the other side, then what will happen? Does the body move? No, body will not move. So when the equal amount of force acting from the other side, this body will not move. This body will remain stationary. So if the equal amount of force acting on the opposite side will not create motions, now you can understand that if I'm applying the force of some Newton on this board and board is not moving, it means the board is also applying the same amount of force on my hand. So that's your Newton's third law. It says that to every action there is an equal and opposite reaction. It means if we apply some amount of force on any body, then that body also apply the same amount of force on us. Like if I'm taking this book, right, I'm holding this book, so I'm applying some force on it upward direction, that book is also applying its weight in the downward direction. That is why it is in stationary condition, right? So that's your Newton's third law. There are so many examples based on Newton's third law, like when you walk, then we push the ground backwards with some force, and similarly the earth also push in us in forward direction, and then we can able to walk, right? So there are so many examples in your book, please read them. Let's see some example based on Newton's third law of motion from your textbook. Let's see some examples of the Newton's third law. The first is a book on a table. I have also give this example on the board. When a book is placed on a tabletop, the book exerts a force equal to its weight W due to the gravity on the table in the direction downwards. Now to react this force, to react this weight of the book, table counter the force and create a force in the upward direction known as normal reaction. So this is one example of Newton's third law. So the second example, pushing a wall. When you exert a force on a wall by pushing the palm of your hand against it, you experience a force exerted by the wall on your palm also, right? That means if you're pushing the ball, this is the action, and the wall is creating a counter reaction on your hand. So this is due to the Newton's third law. Third example, Motion of boat moving away from the shore. When a boatman wants to move the boat away from the shore, he pushes the shore by a bamboo or with his oar. This is the action. The shore pushes the boatman along with the boat away with an equal and opposite reaction, and so that boat can move inside the water. So here's another example. Motion of boat in river. Again, I've given the example in the video. To move a boat ahead in water, the boatman pushes, that is the action of the boatman, the water backwards with his oar, and the water exert an equal and opposite force, which is reaction, in the forward direction on the boat, due to which the boat moves ahead. Right, so if you want to move forward, then you have to move your oar in the backward direction, so that water pushes you in the forward direction. So that's the another example of the Newton third law. Firing a bullet from a gun. When a man fires a bullet from a gun, a force F is exerted on the bullet, that is action, and the gun experiences a equal recoil R reaction, and as shown. That's why when any person fire a bullet, then his hand got a jerk. This is the reaction of the bullet on the gun. Rocket motion. In rocket, fuel is burned inside the rocket, and the burnt gases at higher pressure and higher temperature are expelled out of the rocket through a nozzle. Thus, rocket exerts a force F, that is action on gases, to expel them through the nozzle backwards. The outgoing gases exert an equal and opposite reaction R on the rocket, due to which it moves in the forward direction. Right, this happened with every rocket, astronomical rocket as well as Diwali rocket. Motion of man on ground. When a man applies a force F, that is action, backward by his foot on the ground against the force of friction, the ground exert an equal and opposite reaction R forward on his foot. The horizontal component of the force of reaction R enables to man to move forward. Obviously, it will be difficult for a man to move on a slippery road where friction is less, and that's why people slip usually on an icy road, or where we don't have enough amount of friction. Right, so friction plays a very important role to move on any surface. Motion of boat away from the shore while stepping down from it. In order to get out of the boat, man exert a force on the board of the boat. This creates a force of reaction which enables him to step out of the boat. At the same instant, the boat tends to leave the shore due to force exerted by the man. For the safety of passenger, the boatman ties the boat to the pole on the shore so that it does not move away. Right, so I think you have been observed this. If you ever sit on the boat, whenever you step out of the boat moves in the backward direction. Catching a ball. While catching a ball, the ball exerts a force, that is action, on the palm of cricketer, and the cricketer exerts an equal force reaction on the ball to stop it. And that's why when you catch any ball, your palm get hurt. Right. So these are some examples based on Newton's third law. You've understood. So now let's move to our next topic. So these are the examples based on Newton's third law. Now you understood how the things react when we apply some force on it, right? So this is we can say significance of Newton's third law. Now let's move to our next topic of this chapter, which is gravitation. Gravitation. Gravitation force is one of the four fundamental forces in the universe which tied the universe together. Without gravitation, life on Earth, or we can say anything in the universe, will be split apart. There will be not anything. we can't have our solar system, we can't have our galaxy. Even all the galaxies will flew away from each other. It means all of these matter, all of these planets, stars and galaxy, they attract each other. And this force is known as gravitational force. It's a universal law. In the whole universe, two masses, if we have two masses, then they will attract each other with some force. And this force is due to the masses present in the bodies. Now, what is the amount of force that the bodies apply to each other? And what is the direction of force? It is given by Sir Isaac Newton. He said, if two bodies, suppose we have a body this of mass having, let's say, m1, and the another body of mass m2, and they are separated by a distance r. Now the gravitation force between these two bodies, first he said force, or we can say gravitation force, between two bodies is directly proportional to the product of their masses. It means that F is directly proportional to the product of, that is, m1 into m2. Higher the masses, higher will be the force. Second, he explained his law in 2 points. So first is this point, that force is directly proportional to the product of their masses. And second, force is inversely proportional to square of the distance between them. So here you can see have the distance is r between these two bodies. So the force will be inversely proportional to r square. So he gives his law in 2 parts. Now if you combine both the laws, both the parts, what you will get? Let me rub this first. So when we combine these 2 parts, first part where force is proportional to m1 m2, and second that is inversely proportional to r square, it becomes F proportional to m1 m2 upon r square. Now you can see here it is not equals to, it is proportional to. So we have to remove this proportionality sign and put a constant. So Newton gave the constant capital G m1 m2 upon r square, where capital G is known as universal gravitational constant, right? What it's saying, universal gravitational constant. Please refer to this line, universal. It means the value of G, the capital G, is same everywhere. It is same for Earth, for Moon, for Mars, for Saturn, even if you go outside the solar system, the value of G will remain same. Even if now we are in the Milky Way galaxy, if you go to the Andromeda galaxy, which is the nearest galaxy to the our galaxy, then there also the value of G will be same. So as this universal means, this does not change in entire universe. It will remain same. Okay. Now what will be the value? Before value, let's find what should be the unit of G. Then I will write the value. So unit of G. Okay, so G, you can write the G here. G equals to force into r square upon m1 m2, right? Okay. Now force can be written as mass into acceleration. I'm writing here. Force is nothing but mass into acceleration. Mass means kg and acceleration means meter per second square. So at the when we write the unit of force, we'll write kg meter per second square. So write the units. Force unit is kg meter upon second square, right? This is radius, distance, that will be meter. So this will be meter square into, they both are masses, it will be kg square, right? So what will be the unit now? 1 kg will be cancelled out. It will be equals to meter cube upon kg second square. You can also write the unit in the form of MKS also. So instead of writing the force as this, I can write it as Newton. So when you write the Newton, what will it become? It will become Newton meter square upon kg square. So, or we have one more, that is Newton meter square upon kg square. So these are two units of gravitational constant G. Now what is the value of G? Let's write it, because it is very, very important to remember the value of G, because it will help you to the senior classes also. So the value of G, capital G, is 6.67 into 10 to the power minus 11, and this is unit Newton meter square upon kg square. So this is the unit, this is the value of capital G. Alright, 6.67 into 10 to the power minus 11 Newton meter square upon kg square, and this will remains constant in entire universe. So we have seen the magnitude of force. We can find the magnitude of the force with the help of Newton's formula, that F equals to G m1 m2 upon r square. Now because force is a vector quantity, then it must have some direction also. What is the direction? It is the mass m and mass m2, m1 and m2, and this is the line joining these two masses. Now let's say the F12 is force on m1 due to m2, and let's say F21 is the force on m2 due to m1, right? So they both attract each other. So the m2 will attract the m1 toward itself. This is the force on m1 to m2, that is F12, and similarly m1 will attract m2 toward itself, so that will be F21. So from here you can see that both the body attracting each other in the same line, along the same line, and in opposite direction. You can see here F12 is acting in this direction and F21 is acting in this direction. Now if we find the magnitude, then the magnitude of F12 is equals to F21. That means if the M1 is imparting 100 Newton force on M2, then M2 will also impart the same amount, that is 100 Newton on M1. Right? So forces are equal and direction is opposite. That means they make action-reaction pair. So you must have understand one thing from this discussion, that gravitation force is a mutual force. Suppose we don't have mass M2, then where this M1 will create the gravitational force? Force will be zero. So it's not like that a heavy body will impart more force on the lighter body, or the lighter body will impart less force on the heavier body. No, they are mutually, they attract force mutually. If some amount of force earth are imparting on us, that means we are also imparting the same amount of force on the earth. The attractive force imparted by the earth on the moon is exactly same which the moon attract the earth towards itself. Alright, so this gravitation force makes an action and reaction pair. In the next video I will discuss the significance of the gravitation force, and we'll discuss some more concept regarding this. Till then class, thank you so much.